Depth first search in graph. Depth first search or DFS is a graph traversal algorithm used to explore nodes and edges of a graph. In the last lecture, we learnt about BFS, that is breadth first search. In that case, what did we do? We always prioritized breadth over depth, and this time we are going to do the opposite. What did we do when we prioritized breadth over depth? Whenever we were traversing through different nodes, what did we do? We always made sure that all the nodes or all the vertices that are at a distance of 1 from the source, if this is my source, all the nodes that are at a distance of 1 from the source, 1 means one edge from the source are visited before you move on to any node which is at a distance of 2 edges from the source. So if you have some nodes, let us say here, and you want to go here like this, you will visit these nodes only after completing these ones, because these are the ones which are closer to the source. This is what we did in breadth first search. But in depth first search, we are going to do the straight opposite of that. That is, instead of looking into these nodes, you will keep going as far as possible from the source in single go. So you will go into as much depth as possible, and this is why it is called depth first search. What we will do, we'll take the same example that we took in last lecture and try to understand what is the difference in the path followed when we use a depth first search strategy. So we took a graph like this in the last lecture. This was a graph and we had edges on all these points. So we are going to see what is the difference in the traversal depth first search will bring in compared to breadth first search. This is the source. Let us say A, B, C, D, E, F, G, H. These are the different vertices that we have. First of all, let us write down the order in which breadth first search will traverse. So in case of BFS, what is the order? You will start in the source. Next step is you will go to those vertices which are at a distance of 1 from the source. So A and E. After this, you will go to A and E. After this, what will you do? Let us say you continued from A and E. Next step, you will do all the vertices which are at a distance of 2 from the source. So B, D and F. So let us say you will go to B, D and F. And after this, you will go to those vertices which are at a distance of 3 from the source. So if you see, these two are at a distance of 3. If you want to reach here, you want to go through 3 different edges. For example, if you want to reach C, you want to come as SA, then AB, then BC, or maybe SA, then AD, then DC. So whatever it be, it will take minimum 3 moves. So that is why these are at a distance of 3. So C, G. What is remaining? H is remaining. So H will be the last one. So this is the order you will have in case of BFS. And one more thing, it's not a strict order because A and E can be interchanged. Maybe in some other representation, in some other implementation, E will come before A, or maybe these ones B, D and F, these can interchange. But the only point is anything in this set, this can't come before any vertex in this set because they are at different distances from the source. B, D and F, these 3 are at the same distance from the source, and whenever it is at the same distance from source, those can be interchanged, no problems. So this is the BFS order. We'll see what difference will it make if it is DFS. So when it is DFS, let us say from S you started, you can only move to any adjacent node. You can't directly jump onto any random node. So what you will do, from source, you have 2 options. You can go to A or E because these are the adjacent ones. Let us say I went to A. After going to A, in case of BFS, I would have gone to E only because this is the closest. In case of DFS, what I'll do, wherever I'm standing right now, I'm standing in A, right? From A, I'll attempt to go as deep as possible. So I'll try to go somewhere else from A. So from A, I have two options, D and B, because S is already visited. So let us say I'll go to B. So I went to B. What is the next step? Again from B, I'll try to continue. So what I'll do is, if I hit any dead end while I'm continuing like this, I'll backtrack, come back in the same path, and while coming back, I'll see if there is any path possible from any of those nodes. So this is why it is depth first. After B, I'll go to C. So C. Then maybe I can go to any of these. I can go to D or I can go to H. Maybe I'll go to H. Then from H, I can go to G. From G, I have two options, F or D. If I go to F, then from F, I can go to E. And from E, I can go to D. So this is how depth first search order will look like. See, this is not a single order. For example, when we were learning about trees, in case of trees, whenever I said pre-order or in order or post order, there was only one particular order possible for these traversals. If I say I want to get pre-order traversal of this particular tree, it will be unique. Or if I say in order traversal of this particular tree, the traversal will be unique for a tree. See, the other way is not right. That is, if you are given any particular pre-order or any particular in order and asked to construct a tree, there are multiple possibilities of a tree. But if you are doing from a tree towards the in order or pre-order or post order, there is only one particular output possible if you are getting this from a tree. But in case of graph, from the same graph, you can have multiple DFS orders. For example, after S, instead of coming to A, I could have gone to E. And after E, maybe I can go to D. So a lot of orders are possible. Even after following to some point, maybe I followed S, A, B. After this, from B, I need to go to C only, because from B, there is no other option. After C, I can go to D. That is also possible. Here I can go to D. So all these are possible. There are different orders possible. The only thing is you should go into depth and not the breadth. Okay. So this is the depth first search technique. So how do you actually implement it? That is the next question. Because in case of breadth first search, you were able to implement it using a queue. How did you implement? You had a queue, and in that queue, you kept adding it in order so that whenever you are picking from queue, you know the same order will be maintained. This is how you maintain the breadth first search order. But in DFS, you want to do something else. You want to always go to the node that is inserted last. Or in another way, if you think, whatever is the next call you are going to make, into that particular vertex you want to go. You don't want to go on the same one. So let us see how we can implement this. I'll rub this off. We'll see the logic of implementation, and after that we'll go to the pseudocode. So the logic is like this. Initially, you will start from the source vertex. Always you have to start from source vertex. Next thing is, there is a visited set the same way you had in case of breadth first, because this will help you to understand whether you already visited this node or not. So let us say you started from source. So what will you do? You will add S to this visited set, saying I already saw the source node. What is the next step? You want to go to the adjacent nodes of source. So what are the adjacent nodes here? A and E. But this time you don't have to go to both. You just have to pick any of them and go to one adjacent. Let us say I'm going to A. So when I go to A, I am calling the same function again. If you think like this, what am I supposed to do in A? From A, I again have to see what are the adjacent ones and I have to pick it. Once I reach the next one, what do I have to do? Again, I'll pick another adjacent node from there, do the same thing, which means I am calling the same function again and again, which means there is an opportunity to use recursion. So the best option here is to go for recursion. So how will you use recursion? you'll have a DFS call. In the DFS, initially, let us say you're calling with source. Then in this call, what will you do? You'll automatically call DFS with one of its adjacent nodes. Then what will happen? In that adjacent call, it will take its adjacent node. Then in that node, it will make a DFS call. So this will keep on going recursively. Whenever this sort of recursion happens, it will by default go to the depth. Whenever you have an application in which you want to go to the next one in the depth, then you can always go for recursion. That is why in case of trees, we were able to use recursion because you wanted to go to the depth of the tree. This is why you used recursion in trees. So the same way, let us understand the recursive algorithm. I'll rub this off first. Let us do a DFS recursive algorithm. First, we'll think about the steps so that writing will be easier. So the first step, you want to select a source node and mark it as visited. You will also have a visited set. What will you do next? Next is you want to go to each of the adjacent nodes of source. And what will you do in the adjacent nodes? You will pick one adjacent node and then you have to repeat the same process that you did on that adjacent node. That is, once you got this adjacent node you will add it to visited list. Then you will see its adjacent nodes. So you are going to do the same process again and again after that. So this is what we are going to convert into code. So DFS, depth first search of, you will have a graph. So this is your graph. What else do you have other than graph? You should have a node, that is the source. So I'll call it source or node. So initially you will be passing source to this. See, I am not directly writing it as source because in the recursive calls, we'll be calling the next nodes. So I don't want you to be confused by writing source. That is why I'm using a generic term node. Next thing is we have a visited set. The same way we used in breadth first search, same purpose. Inside this DFS algorithm, what should you have? First thing is you should check whether the node is visited. So how will you check? If node, the value of node, if this is not in visited, you can continue. If it is visited, that means you already visited this, you no more have to call again with the same node. So if node is not in visited, if it is not in visited, then what should you do? Then you should, first thing, you know it is not in the visited list and you are going to check it right now. What will you do? You have to mark as visited. And before that, if you want to print, it is okay. You can, let us say, print node and then you can mark it as visited. So mark, or you can say add node to V because it is not presently in the visited list. So you added node into V because presently you are visiting this node only. What is the next step? You visited this. Next thing, you have to take all the neighbors. So for each of the neighbors. So let us say each neighbor in, where do you get these neighbors from? You get neighbors from the graph representation provided as input. So you will use neighbors in graph of node. So whatever be the list of neighbors, let us say you will get each of the neighbor in this loop. What will you do then? For each of the neighbor, you have to call DFS call. So you will call DFS. Inside that, what are the arguments? Graph, it is the same graph. What is the node? Initially, you were using the present node. That is, in the first call, it will be source. After that, whatever it be. So whatever is the node you are presently looking into, next time you should be looking into neighbor. So here you should put neighbor. So this is neighbor. And then you should also pass the visited list because this is what helps you determine whether you should run this particular function for this node or if this node is already visited. So this is the DFS algorithm. What is this algorithm doing? See, because it is recursive, it is very easy and convenient to write. Moreover, it looks logical. See, what is it doing? It is initially checking whether you already visited. So this is your visited list. So if you already visited this node, it will be marked here. If it is visited, that means it is done. You don't have to run algorithm again on that. If it is not visited, print node, print the value, whatever. After that, you can add it to V, that is to the visited list, so that you don't visit it again. And this is the most important step. What are you doing? You are checking for all the neighbors of the present node, whatever be the neighbor. For all the neighbors, you are making the same call. So what will happen? Let us say you have 4 neighbors. So you will call 4 times. I will call it as D1, D2, D3, D4. 4 times I'll call here in this loop. But when I make the first call, let us say I'm in this loop, I made the call to the first neighbor. What will happen? It won't let this loop run the second iteration. So these things won't happen right now. What will happen first? First execution of the first call happens because you are presently at this point, you are executing function on one neighbor. So it won't allow you to go to the next iteration of the loop in order to call for the next neighbor. Instead, present function that is called on this neighbor will go into the depth. It will call its neighbor, then again its neighbor, and so on. That is where it is depth first search. And one more thing is, if you want to try out an iteration, then what you can do is, in the last time when we learned about breadth first search, we used a queue, right? When we used a queue, what is the advantage that we got? Let us say you have 3 adjacent vertices for any particular vertex. So you added those as A1, A2, A3 in the queue. So after this, whatever you may add, these adjacent ones will be visited first because this is a queue. So whatever you added first, they will be visited first. This time, what do you want to do in case of depth first? You actually want to do the opposite of this. Whatever you added last, you want to visit that first. So what is the data structure you should use? Instead of queue, you should be using stack. So if you use a stack, the same logic that we use for breadth first search, the same sort of iterative algorithm, if you use a stack instead of queue, what will happen? Let us say you have 3 adjacent vertices. Then you will insert A1, A2, A3 into the stack. What happens next time? You will take whatever is on top. Let us say you took A3. After this, what will you do? You will add A3's adjacent vertices. So let us say B1, B2, B3 are A3's adjacent vertices. After this, what happens? Next call happens with B3. So this is what you should do in depth first search. So this means in case of the breadth first search algorithm, if you want to use a similar algorithm for DFS as well, just use the same algorithm, but you can use a stack instead of queue. Okay. So that is what you have to do. The next thing is we have to understand the time and space complexities of this algorithm. What is the time and space complexity of this depth first search? Do you want me to run this once? Let us do one thing. Let us try a dry run on a very small graph just to understand. If this is my graph, this is the source, then I have A, B, C, D, E, F, G and H. What will happen here? Initially, I will make a call with source. So my source is visited. After this, what happened? My visited list is here. So source is visited. What is the next thing? From source, I'll reach this point. What will happen at this point? From source, I'll call for A. Let us say A is my first neighbor. So I'll call for A. So I first called DFS from source. From source, when I'm calling in this loop, it will call for A and E. 2 calls are required. But as soon as A's call is done, the run for source that was going on, that will halt there. And what happens? A recursive call will be made For S means this is actually DFS of S. DFS of S. This is what I have to write. I am simply writing S. I hope you understand. So after this, when S execution is going on, I will call DFS of A. So what happens? S execution will be halted. DFS of A will continue. In DFS of A execution, what happens? So in S execution, there is DFS of E remaining, but that will happen in second iteration of this loop. Presently, I am not letting it go to second iteration. In the first iteration, it is halting here. It is making recursive call to A's. So DFS of A is called. What happens then? I'll go into A's neighbors. Let us say B, D and S are the neighbors. So what if I call for A? Maybe it will recursively call B, DFS of B. So like this, in recursive stack, it will keep a track. That is why I told you, if you are using iterative algorithm, you have to explicitly maintain the stack and use it. If you are using recursion, automatically it will be done. So this is not a case where using iteration will decrease your space complexity. We had seen in case of trees that there are some algorithms in which if the space used is purely because of recursion stack, then it may be possible that when you convert recursion to iteration, you may save some space. Your space complexity may come down. But in this case, you actually need that recursion stack in order to keep track of what is going on. So if you convert recursion to iteration, what happens is you will have to explicitly maintain a stack which will work like the recursive stack. So kind of you will have to mimic the recursive stack. This is the situation in DFS. What we will do is, so here what happens, like this it will keep adding on recursion stack. So this is how it will go into the depth, right? That is what happens in depth first search. What is the time complexity? Similar to the BFS time complexity, here also time complexity depends on what is the representation you are using. If you are using adjacency matrix representation or adjacency list representation. Let us consider adjacency list representation. Then what happens? In case of adjacency list, time complexity is order of V plus E, and this is for the same reason we discussed in BFS. What is the reason? Order of V is required because you want to go to all the vertices. What is the purpose of this whole traversal? This traversal is going to all the vertices once, and you know that it will go only once because you have a visited array. Because of the visited set, what happens? You are going to go only once to each vertex. So order of V is contributed by that. Where is this order of E coming from? The same way it came in the previous case. Here you have a loop for finding all the neighbors. So because of this particular line, the remaining will be called only when you have not visited, which means only once these procedures will be called for each node only once, right? For each node, you have to find all the neighbors. So if each node, if you find all the neighbors in adjacency list representation, what happens? You have an array of pointers and you have a linked list of all the adjacent nodes here. What happens right now? If you want to go to all the neighbors of all these, you have to traverse through all these nodes that are present. In total, this will be order of E. Why? Because each of these represents an edge. If this is corresponding to A, this is corresponding to B, and this is C, then this represents edges AB and AC. Similarly, whatever edge you may be having, representing that, there will be an entry in adjacency list. Because of that, total number of times you have to do work, that is, total number of neighbors present will be order of E. So total time complexity is whichever be higher, vertices or edges. So it will be order of V plus E. That is the time complexity. What about the space complexity? And this we are presently considering adjacency list representation. What about the space complexity? Again, the same way we discussed for BFS. Space complexity is order of V because you are maintaining an extra visited array. So it can at worst case go to order of V. What if it is an adjacency matrix representation? If it is adjacency matrix representation, this step, which is looking at neighbors, that is going to be costly. The same reason that we discussed in last lecture, order of V times you have to look into neighbors, because for each of the vertices you will be looking into neighbors once. So order of V times you have to look into neighbors. What time will it take each time? Because it is an adjacency matrix, if you want to identify neighbors, you have to go through one complete row. One complete row is order of V. So order of V times order of V, which is order of V into E. Order of V square is the time complexity in case of adjacency matrix representation. One more thing is, this is also the reason why we say that you should use adjacency matrix if it is a dense graph and adjacency list if it is a sparse graph. What is the reason? Let us see the time complexities first and let us compare these. So in case of time complexities, for adjacency matrix, we saw it is order of V square. This is for adjacency list, okay? So in case the graph is dense, what happens? Order of E is equal to order of V square if the graph is dense. Because if you, how many edges will you have if almost all the edges are already put? Total number of edges will be order of V square, vertices square, because from each vertex you can have edge to all other vertices. That is, if total vertices is V, you can have V minus 1 edges on each of the vertices. If you are having self loop as well, then you can have V edges. So if each of the V vertices are having order of V edges, total number of edges will be order of V square. That is, if the graph is very dense. If the graph is dense, order of E is order of V square, which means this will be order of V plus V square, which will be order of V square only. So there is no specific advantage of using adjacency list if it is dense graph. But if it is a sparse graph, then there is advantage, because if the graph is sparse, then order of E can be considered as order of V. In that case, this will come down to a total of order of V, and adjacency list representation will be better in case of time complexity. Otherwise, if it is not, then you need not choose for adjacency list. You can go for adjacency matrix.